Welcome and thanks for joining us. My guest today is Pat Maharg. He's the chief architect for model-based systems engineering at Noblus. Pat, good to have you with us today.
Thanks, Tom. Nice to be here.
And I want to just set and define some of the terms a little bit. Model-based systems engineering. The word I'm hearing a lot in the military complex, especially, is digital engineering. And are they the same things, or are there subtle differences? Tell us, let's set the terms here.
So, Tom, digital engineering is much broader, and it sits at a higher level of abstraction than model-based system engineering. Digital engineering is both the business process, the engineering piece, and then how those programs are actually moving from paper-based to digital products. Model-based system engineering is part of that, and it's an enabler. And it also supports, from a system engineering perspective, it's our next step to that digital engineering.
Got it. And so it's, on the other hand, it's a lot more than simply, as we understood CAD to be for the past 30, 40 years.
And that's a great example. CAD, for instance, is also a part of that digital engineering transformation as well. So we're moving from paper-based documents in the past to digital artifacts that we can share amongst other engineering disciplines.
Got it. So tell us more about model-based systems engineering then.
So model-based system engineering is a natural progression of system engineering. And system engineering has been around since probably in the 1950s and been practiced. And so that's our next step on creating digital products instead of paper-based products. So model-based system engineering captures our products, our system engineering products, in a model.
And is this only for the physical world, or is it also for the cyber world?
So that's a great question. So it's for the complete system as a whole. So it can include the physical parts. It can include the software. It also includes the mission or the operation of the system. What do you use it for? How does it behave in the real world? How does it interact with the human beings that operate those systems?
Because, you know, I've just been to a couple of military test ranges by coincidence, and I saw an object that had gone very, very fast for very, very long distance, and they were testing the system that would make that happen. But also they needed to know the parameters and what would happen to that object as it went that fast and that far and gets hot and so forth. And so embedded in it were a lot of data gathering tools and sensors inside. So you had a physical system that had to do certain things, but then they had to understand, to further develop the physical system, they needed a data system to go with it. And ultimately this will have to do with how they can field a practical system for warfighting, you know, transferring it from a test bed to, you know, an actual operational system. So how would it sounds like they were doing model-based systems engineering there.
So that's a great example. So model-based system engineering, we start at the beginning of what we call the requirements, or what the user or the stakeholder really needs the system to perform or do. And we capture those in that model. And over time, we'll develop what that system looks like in what we call a digital twin. So that digital twin gives us a lot of flexibility to create 1, 2, or 3 different variants of that system. And once we create those variants, we can take a look and ask, you know, the customer or the stakeholder, is this really what we need to do? So instead of building many, many prototypes, we do it in that digital environment, and we can do it very quickly, as opposed to creating something in the physical world can take some time. So once we think we've got it right, then the customer can decide, yep, we're going to build a prototype at this point. And what that does is it compresses the schedule, and it also helps us to understand the system at a much lower level before we actually build that prototype of the system itself.
And how do you ensure that the digital model that you build, or the twin that you build, which in some sense comes before the actual thing, is conformant to what we know about physics and material science and all of those things? You could build a digital twin of an airplane that can fly backwards or something. You can do anything in digital, but how do you know that it conforms to what is possible with real world physics?
That's a great question. So when we create these models, the modeling team, really the system engineers are capturing a lot of the data of the other disciplines that are involved in building the system. So we're the data gatherers, you can think of it. So what we're trying to do is we interact with all these other engineers that are trying to build the system. We capture what we think they're trying to tell us, and then we bring it back and we conduct what we call a peer review. And the peer review is with the subject matter experts that take a look at the model, and we look at the data, the math, the parameters, and those things that we've collected to make sure that we've got it right. The other key thing that system engineers do is also, I call it, we're the glue between the disciplines. So you may have an aero engineer or an electrical engineer. Somebody has to sit between those two disciplines and make sure that we're all on the same page building the same system, and somebody doesn't do something that affects somebody else in a negative way.
Right. You could have a thermal effect from the mechanical system, which would harm the electrical system, for example.
Correct.
But the
Yep.
mechanical guy may not know that.
You're exactly right. Spot on.
All right. And we were talking also about modeling software systems. And I mean, for many years, people have designed software systems with a set of inputs and outputs that they want at the end. How can that be enhanced? Because in some ways, building software systems is just as daunting as building things that fly or go under the ocean.
Correct. So the software systems, from a system engineering perspective, we capture them in the same techniques in the model. So from our perspective, we think about systems from an abstract level. And when we start to build these models, we think of four areas: the requirements, or what the stakeholder needs to do; the interfaces, or how these parts of the system interact with each other or talk to one another; and then how do they talk to things outside of the system; the behavior, or how the system operates or interacts with a human being or on its own; and then what we call the structure. And the structure is the parts. So when we design a system, we say these are its parts, or there's 5 or 6 different subsystems or segments that we're going to glue together to create the system to meet those requirements.
Right. So that I imagine that requirements drive everything, of course, in especially in federal systems planning and in development. But often the requirements get modified, and that causes delays and so forth. Is it possible, using this type of model-based systems engineering, to maybe refine your requirements early on, and then as you move through the process, you've got a much smoother pathway because you don't have requirements that need to be modified, or requirements that can't really be met within the cost parameters you might have for the project?
Yeah, that's a great question. So model-based system engineering, the requirements, what I say, don't stand alone. And in the past, in system engineering, we had the requirements in a document normally, and then we had other things that were designing the system, and they weren't tightly coupled. So in a model-based system engineering approach, our requirements are also tied to those interfaces or to the behavior of the structure. And we can quickly do an analysis, just like you said, of normally change. Change is a normal thing in the systems engineering, especially in DoD. We have either new capabilities that are coming in, or we get a constraint on cost. We don't have as much money as we thought we did. So using the digital twin model, we can quickly look at that requirement and say, if I remove this requirement, what is the spider web of this requirement? How does it go out into the model, and what is it going to touch and affect? Then we can present that through analysis to our stakeholders, our customers, and say, if we remove this, this is the impact of that system. Before we had model-based, we had to basically do it through analysis in a paper documents, and it's very difficult to start to trace those. If the system has been under design for a year or 2 years, you have many specifications at lower levels that aren't connected sometimes, so it makes it very difficult to do that analysis.
And getting back to the interface question,
Mm-hmm.
want to understand the interfaces within the given system that you're designing. But what about system to system interfaces? For example, if you design, and keep returning to the, say, the aircraft platform or the ship platform, and often they change out systems on those platforms. But the system to system, the existing system, the platform, and its interface to the new system, that's also an issue, I imagine. in using this model-based development.
It is. And the beauty of model-based system engineering is I can attack the problem at different levels of abstraction. And so from um, a mission perspective, or we call it an enterprise perspective, an aircraft to an aircraft, those two aircraft need to communicate through those interfaces during a mission. Sometimes in the past, we just created the aircraft and we didn't take into consideration how does it talk to other things within that theater of battle or the environment. So that lets us move up and down in the levels of abstraction of those interfaces and actually define and describe in detail what those two platforms are going to talk about through that interface. We capture that in the model. The beauty of that is those interfaces now are in the model and the model lives on. And in the past, we would create a system, document it at that point in time, and it was almost frozen. So if we had to go back later and add something to it or change it, it's very difficult and it's time consuming to go find all those documents, glue them all back together because the team that built it has now been dispersed.
And when you think about parts, as you mentioned earlier, as one of those elements here in the model-based systems engineering, when you're talking about software, what's the analog to physical parts for a electromechanical system?
Mhm. So it's the same concept, how we think about it in model-based system engineering. Software has a much higher refresh rate. And what I mean by that is we're continually patching and updating software. So if I have a good model of the software architecture, I can look at those interfaces. And if we have a vulnerability in a piece of software, the first question is, how do I take that piece of software out and replace it? Mechanically, we can go touch those things and look at it. A software, you have to put it in something visual that human beings can consume. And a model approach can do that very quickly. So we understand the interfaces and how it interacts with other software applications within the system if we have to replace it or update it.
It sounds like this whole process is a way of getting better return on investment in systems development.
I agree. And once we build, the beauty of the model is now it's going to travel through the life cycle. And what I mean by that is most of our capital investments in DoD, for instance, aircraft carriers, submarines, they have a very long life cycle, 30, 40, 50 years, as opposed to iPhones. iPhones, about every 3 to 5 years, you usually have to get a new iPhone. So we're building systems that we know in the future, we're going to have to go back and revisit and change those. And the model gives us a place, once again, to collect that information that will travel with the physical system throughout that life cycle until we dispose of it.
All right, I want to explore that a little bit more, but right now we're going to take a short break. My guest is Pat Maharg. He is the chief architect for model-based systems engineering at Noblis. I'm Tom Temin. This discussion is how to benefit from model-based systems engineering, sponsored by Noblis here on Federal News Network.